Okay, so moving into 6.4 now, we're looking at applications of vector addition. So this is really the application part, like what it might look like more in a real life situation, right? So we're talking about a boat or a plane, just as examples. There's several forces acting on it, right? So whether it's wind, whether it's the current of the water, gravity. So some key ideas to start: when I have two vectors that act on an object at right angles, so perpendicular to each other, I can use vector addition. I can use Pythagorean theorem, which we'll go over, and I can use trig ratios, which we'll also go over, in order to find the resultant vector. So again, this is only in cases when the two vectors are at right angles. So Pythagorean theorem, pretty straightforward, right? The longest side, the hypotenuse squared, is equal to the two shorter sides squared added together. Also, just to go over, if you're labeling your diagrams, right, the angles are capital letters and the sides are lowercase letters, and the sides are always opposite the angle. The side and angle letters are opposite to each other. And for trigonometric ratios, we're looking at, let's say obviously we're talking about angle A here. So just to kind of say, I would teach my class and say, pretend there's a little version of you standing in there. So I'm standing in angle A. The sine of A would be equal to little a over little c, meaning this side over this side. And the reason being is because it's right opposite over hypotenuse. So again, this is where you use your SOHCAHTOA. And if you need more review of that, you could always, from home, YouTube or Khan Academy, primary trig ratios, or just ask me if it's in class or during math help. And this would be true also for, we could look at angle B, or we never stand in the 90-degree angle. Okay, so when I'm doing primary trig ratios, those, it's only the two angles, it's never the 90-degree angle. So we could do things from B's point of view as well. But you guys let me know if you need further help with that. So when two vectors above, it was talking if they are perpendicular to each other, right? So again, if they're perpendicular, it's going to show you, or it's going to say something is horizontal and something is directly vertical, where you know you can put a 90-degree box in there. This is the case. Well, what do I do if I have a diagram that's not 90 degrees? So when two vectors do not act on an object at right angles, then I can still use vector addition, but then I would have to use, just like we did in grade 10, sine law or cosine law to find the resultant, because that's what we use when we can't use primary trig ratios. So just again, a review of sine law. Again, the lowercase is the side, and it's always the sine of the angle. So whether this is in the denominator or in the numerator, the sine, it's always sine with the angle. And I would just say, to make life easier, though, you probably have the way that you are used to doing already. So you could do either one. I could just say, I would just memorize one of them, let's say, and you can just always use it this way. So whether you're solving for a side or an angle, you can always use this formula with the lowercase on top and sine of the angle on the bottom, rather than worrying about, am I solving for a side? Am I solving for an angle? And deciding which one of these formulas to use. They're the same thing. Once you set two fractions equal to each other and you do cross multiplying, it's going to end up being the same thing. So I'm just saying you could just go with the same method all the time. And for cosine law, it depends on what angle or side it's asking you to solve for, right? So if it was asking you to solve for angle A, let's say, then you would have this formula: a squared equals b squared plus c squared. So that's Pythagorean. And then minus 2, it's always minus 2 times whatever's on the right side. So minus 2 times BC. And then cos of, this is the only angle, this is the only capital, cos of whatever was out in front. So if it's side A out in front, it's always angle A. So see how this is side C out in front, then it's always cos of capital C. And this does matter because you're getting these values from exactly where they are in the triangle. So again, if you need more help with cosine law or review of that, just let me know. All right, so we're going to be seeing words like ground velocity. So ground velocity basically just means the resultant. So it's the velocity of an object relative to the ground. So if it's asking you to solve for the ground velocity, it's asking you to solve for the resultant. So to solve for the resultant means that I want to solve for both a magnitude and a direction, right? Because it's a vector, resultant vector. It needs to have both. And we will see examples of this coming up shortly. The equilibrant vector, which we'll just call capital E, the E vector, equilibrant vector, is a vector that keeps an object from moving, which is just the opposite of the resultant vector. So just using this as an example, I have vector 1 and I have vector 2, and I have it set up as a head to tail method here, right? So I have tail to head, and then this tail to vector 1's head, tail to head, and the resultant is you start at the beginning of vector 1, going to the end of vector 2, or where the head is of vector 2, and that is your resultant vector, right? So if that's all there was, then the resultant's force would be moving in this left direction, because it is starting here and ending here. So it's going in the direction of a force moving left. But by placing a vector in the exact opposite direction of the resultant, so hence this red one here, we're going in the exact opposite direction of the resultant. If I were to add those together, it would give me 0, right? They're the same length. They're opposites of each other, so a negative and a positive version of the same thing. I would get 0, which results in a 0 vector, and that is what causes the object not to move. That is what causes the scenario to not be moving. So this is my equilibrant vector, and it's always opposite directly to the resultant vector. And when we're talking about, just to give a further example here, keeping an object from moving, and we're going to look at this example next, which has got me thinking about just kind of saying it now. We're going to be doing an example about a traffic light. So if you think about a traffic light that's hanging there, right, as you go through the intersections, gravity is trying to push it down. However, there's also something holding it up. So you've got something acting in the opposite direction of gravity in order to hold it up, and that's the idea of an equilibrant. So let's look at some examples here. Determine the resultant of the vector sum. So we're going to look at this vector and then sum them together. So we are dealing with vectors though, even though we don't have anything written with the vector symbol on top, because why, right? Think about it. We know that, here, we know that this, oh, got my pen. We know that this is a vector, and we know that this is a vector, because they both have what? They both have magnitudes, magnitude, and a direction that they are going in. And so that's how we know that they are vectors. So we are going to do the tail to tail method here, which will work most of the time. The only time it wouldn't work is if the vectors are going in opposite directions or going in the exact same direction, right? So as long as they're going in different angles and creating basically a triangle that you could get out of them, you can use the tail to tail method, as I'll show you here. So first though, we need to look at both of these, let's say magnitudes, and come up with a scale as I start. So let's say our scale would be, what do you think? We're going 2.5 kilometers, and then we're going 3.5 kilometers. So it doesn't need to be that large. So we could just say 1 centimeter equals 1 kilometer. Because we can draw something that's 3.5 centimeters long and 2.5 centimeters long, right? So let's draw our directions here. I'm going to try to do that a little bit better, or just use, I deleted everything. Here, let's just quickly throw the scale back in there. Not too much to write out. So the scale is going to be 1 centimeter equals 1 kilometer. And then I'm going to use, let me check out here. I don't think I have compass draw. No, I can't draw like a cross. I can just use a straight line though. So north to south, west to east. Okay, so, and let's put those in our compass directions: north, south, west, east. And so now let's read the first one. So I forget, I think that one was a dark green, let's say. So that's what color we'll do it. So I'm going 2.5 kilometers. So I'm looking at, and I should get my ruler and do 2.5 centimeters exactly north, starting north and heading west in a left direction, 45 degrees. So we already know that if this is 90 degrees here, right? 45 degrees is basically exactly the diagonal that cuts that quadrant in half. So let's see if I can do a good job on that. I've got a green. So roughly, and this one is the shorter one. Let's say 2.5 kilometers, 45 degrees. Yep. And then let's do dark blue. Oops. I'm just going to leave. No, I'll erase that. Now that I've got it twice there, I don't want to confuse you. Okay, so back to my pencil. All right. And then we're going to look at this one, which is starting south, right, and heading west. So starting at the bottom and heading left. Again, the same 45 degrees is also cutting it in half. So if I start here, we are going in a, but we're going 3.5 centimeters. We want to draw one that's 3.5 centimeters long. So it should look a bit longer. And again, you should get a ruler and actually do it properly. And then when I finish off, to create my parallelogram, to do the tail to tail method, right? You have to finish your parallelogram. So I wish I could do a dotted line, like where I'm, but I'll do my best here myself. Just know that it's going to be off a little bit because I can't really get, there's no ruler in this program. But you get the idea, and then just go straight a tad bit off. But a parallelogram, again, all the corners should be 90, right? Which means that this corner here that we're talking about should be 90 degrees. And so my resultant vector, which I'll do in red, is again starting at the, where the two tails meet and going to the opposite corner of the parallelogram. So starting where the two meet and going to the opposite corner of the parallelogram. Let's say something like that. And again, if I'm off, which we'll see at the end of the question, you know, the reason, the more accurate you do your diagram, if I'm off, it's because this isn't 2.5 centimeters and this isn't 3.5 centimeters. And I'm not, you know, perfectly, if I used a compass, 45 degrees, right? So again, if you're drawing, you're trying to match it to what your numbers are saying, trying to figure out if that makes sense, if your answer is correct. The only way to really know if your answer is correct is to use an actual compass and ruler. And that would make sense that, you know, if this was, you know, let's say 10 degrees below the horizontal here, that's what it would look like, right? Or if you get an answer of 70 degrees below the horizontal, that one wouldn't make sense based on the drawing, right? So I'm just saying it does matter in chapter 6 to have the diagrams as accurate as possible. So let's put in our values. So this green vector is 2.5 kilometers. And this blue vector is 3.5 kilometers, which means that the opposite sides would be the same. 3.5 kilometers and 2.5 kilometers. All right, so to solve now for my resultant, it's really up to us. I can choose whichever triangle I would like to use. I can choose the top triangle, so between the green, the resultant red, and the 3.5, or between the resultant red, the blue, 3.5, and the green, 2.5. I usually in the questions will have a choice of which triangle to use. So I'm going to focus on the bottom triangle, let's just say for this example, and put my theta there. Okay, so I'm going to change back to black. Technically that should be black. It's nothing related to the 2.5 kilometer vector. So in order to find the magnitude, which we will start with first for this resultant vector, and let me just label it R, right, my resultant vector. In order to find the magnitude, let's look at this triangle only. I know this side and I know this side, right? But, and so I have my resultant vector here. So we now know we have to find the hypotenuse. And we know that in a parallelogram as well, we didn't write that in yet, but in a parallelogram as well, I think I said it though, that the corners are all 90. Because this isn't 90 degrees when I pertain just to the bottom triangle, just to this triangle. But this corner is 90, meaning that I could still use like primary trig ratios, or in this case, again, because I know the two sides, to find the hypotenuse opposite the 90, I can just use Pythagorean. So my resultant then Pythagorean is squared, right? Would be the one side, doesn't matter which one is first, 2.5 squared plus 3.5 squared. So 2.5 squared, go ahead, punch it in, is 6.25. 3.5 squared is 12.25. When I add those together, I get 18.5. So again, to get the resultant vector and get rid of the squared, I take the square root, which is going to be equal to about 4.3, and this is in kilometers. Okay, for the magnitude, 4.3 kilometers is the length, let's say, of the resultant vector. So I've got the magnitude part, but now I need to find out the bearing part, the angle part, the direction, in order for it to be a resultant vector, right? So in order to get the theta here, again, we said this triangle here at the bottom, I do have a 90 degrees, so I can use primary trig. So if I was standing in theta and standing in this angle, I do actually have numbers for all three now, because I know that the resultant is 4.3. So I could choose sine, cos, tan, it wouldn't matter. But my advice to you, where hopefully you remember this advice from grade 10, is let's say you calculated this incorrectly, right? The information that the question gives you is the best information to use to solve for an angle if you're able to. So if I have these two pieces of information, I'm going to use that instead of the answer I got for the resultant. So using the 2.5 compared to my theta is opposite, and the blue vector here is the adjacent. So I'm using opposite and adjacent. So in SOHCAHTOA, that would be tan, right? So tan of theta is equal to opposite, has to be 2.5 on top over 3.5. And I'm getting an angle. So again, angle theta is going to be, if you remember, the tan inverse of 2.5 over 3.5. Okay, so do that on your calculator, tan inverse, and you should have about 35.5 degrees. So we have to be careful because that's only theta there, right? That angle is 35.5 degrees. So let's go. The question was in, because I'm just looking at doing my conclusion here now, right? Because I have my direction and I have my, I have my direction here and I have my magnitude here. So all it asked me to do was determine the resultant. So getting those two pieces of information, I have my resultant, but I'm just going up and looking that the answer was given in quadrant bearing. So you should always kind of answer the question the way it was given. So I should answer my question using quadrant bearing as well. So I can start by saying, I'm just going to go up here. Therefore, the resultant vector is Therefore, the resultant vector is 4.3 kilometers at, but for the direction, we need to change it to a quadrant bearing, like I said. So we have our, let's just take a look here. We know that this is 45 degrees. I didn't write those in. I should have probably wrote those in. So let's change this to green. This here angle is 45 degrees. And this angle here, right, is, I'll put it in here, 45 degrees. So if I'm trying to get the answer for in quadrant bearing, then I have my 45 degrees, but then I also need to add the answer that I have, my 35.5 degrees. So if I have starting south, let's say, just because I chose the triangle at the bottom, then I'm saying I might as well go in the direction of south to west is why I chose that. So starting south, I have this chunk, which is 45 degrees, and then this chunk, which I just figured out, which is 35.5 degrees. So at just kind of off to the side here, just to explain that, right? I have my 45 degrees plus my 35.5 degrees. So that adds up to what? 5 and 5, 80.5 degrees. But I have to say starting south and heading west. So the resultant vector is 4.3 kilometers at south 80.5 degrees west. Okay, so let's move on to a second example. Yes. Two astronauts use their jetpacks to maneuver apart for the space station into position. So the first astronaut is applying a force of 750 newtons horizontally, and then a second astronaut is applying a force of 800 newtons vertically, relative to Earth, we're talking about. Determine the resultant force on the part that they're maneuvering. So these directions, if you notice, compared to the first one, are not given in a quadrant bearing fashion. And they're actually a little bit vague because they're not even in true bearing at all, right? It just says horizontally and then vertically. So it is a little bit more vague. So horizontal, it doesn't say if I'm moving to the left or to the right, and vertical, it doesn't say if I'm moving up or down. So that's kind of up to you which direction that you want to do it in. So if I look at just a color code here again, let's say the first astronaut applies a force of 700, oh, my pen, 750 newtons horizontally. Let's say that that would look like this vector here. Oops, horizontally. I'm working ahead of my diagram doing the other one. 750, let's say roughly like that, trying to be horizontal there. And I'll put that in later, the numbers and everything. And well, the second astronaut applies a force of 800 newtons. I did it again vertically, which would be again going completely north. Now 800 newtons is more than 750. So I have to make it a little bit longer, right? I'm thinking this is, I'm just going to start over here because I'm going to, once I do my parallelogram, I'm going to be into my words there. So let me start over here and put in my north and south. I don't think we'll need too much room for the math, I mean, so I can have the drawing take up this space on your page as well. And draw in my north, south, west, and east. And now let's go back. So the green, and we need to scale. So obviously 750, I need my scale to be more than just kind of a 1-to-1, converting it to centimeters. So let's say our scale would be 1 centimeter equals, well, one is 800 and one is 750. I probably don't want to draw more than like, 5 centimeters, let's say. So if I made it, for example, 200 newtons, then I have this one being 4 centimeters, right? And then converting this 750 newtons would be 3.75 centimeters. So that's okay in length. And again, the more accurate you draw these using a ruler, the more accurate when you get your answer, you'll be able to exactly match it to the diagram, right? So 750 newtons horizontally, I'm trying to do roughly 3.75 centimeters. And I'm just going in this horizontal direction rather than going left. I'm just going right. Sorry, I thought that was on my vector. So 750, let's say, is that far. And then because I used blue already, I will use pink. The second astronaut applies a force of 800 newtons vertically. So I just have to make sure that I draw it vertically north and that it's longer, or 4 centimeters. So it has to be longer than my green vector, than the horizontal vector, which again, I should be using a ruler. This should be 4 and this should be 3.75. So then let's do our resultant vector in red. Let's just keep that common. So then the resultant vector is again the tail to tail method. So first I need to draw the rest of my parallelogram. Coming this way and this way. And then I've got 90 degrees, right? Everything is 90 degrees. I don't have to put that in. And then the resultant vector is from where the two tails meet to the, that isn't the result, to the opposite. I was trying to do the actual arrow here. Sorry, I didn't know I didn't have it, but that wasn't too bad. I'm just gonna leave it and put the head at the top there. Okay, and then I need to write in my units. This was 750 newtons. This was 800 newtons. And my resultant vector, I should label it as my resultant vector. And I should also label the opposite sides, let's say too, right? So that this side would be 800 newtons, just so I know, and that the top would be 750 newtons. And what else is missing? Determine the resultant force on the part. So again, to figure out my resultant vector, I will have my angle theta here, and I will use that triangle. So again, you get to choose which triangle. I'm just choosing the bottom triangle. You'll see when we get into chapter 7, we kind of, well, the rule is that we always have to start from the horizontal and go counterclockwise. So just to kind of relate to that, but otherwise, I mean, for chapter 6 here, you could have chose this triangle as well. So just for me to keep things consistent, flowing into chapter 7, I'm just going to choose this triangle because that's what we'll be using in the future. So what information do I have looking at this angle and looking at the resultant? I have this side and I have this side. So I have an opposite side and an adjacent side. So that seems like I can be using tan in the future, but I like to get the magnitude first. But again, I have 90 degrees within the triangle and I have two sides. So I can go ahead and use Pythagorean again then, right, to solve for the resultant vector. So the resultant vector squared would be equal to, again, whichever one you want first, 750 squared plus 800 squared. Those are going to get big. I'm just going to square them and add them both together. You guys can go ahead and add that extra line in. I'll just say that once you square them and add them both together, it's going to be 1,202,500. And so then to get the resultant vector, we need to get the square root of that, which is equal to 1,096.6 newtons. Just make sure you're plugging in and getting the same thing, 1,096.6 newtons. So that's the force, right, of the vector. But we need to say what direction it's going in now, right? So we already said, because of theta here, that I can use tan, and because of the 90 degrees. So then I have tan of theta is equal to opposite first, 800 over the 750. So then angle theta is equal to the tan inverse. I always use inverse for angles, right? I'm going to erase that, of 800 over 750. Go ahead, work ahead of me. That's a 0, 750. So you should get an answer of 46.8 degrees. Okay, so I think that's all the information that we need. We can go right to our therefore statement. So therefore the resultant, so determine the resultant force on the part. So therefore the resultant force on the part is the resultant force on the part is 1,096.6 newtons of force at, and again, this wasn't in quadrant bearing or north bearing, so we can just use the angle that we had, but we need to give a direction. So at 46.8 degrees, let's say above, or you can use the word from the horizontal, but I'm going to explain a little bit further above or from the horizontal once I write this out. Above the horizontal. If I just said from the horizontal, if this is my horizontal, let's say, right, this green resultant, or this green, I'm sorry, vector, then if I could be above it 46.8 degrees or below it, right? From the horizontal could be below as well. So really, I like above is just more specific. I know I'm starting at that vector and moving above the horizontal 46.8 degrees. Just tells me that my resultant is exactly there and not below. I think it's more specific. Okay, let's see. I've got one more example that doesn't take too much time. I don't know how long this video is going. And then the next example is going to take a little bit longer, I feel like. So again, just for time and taking a break, I'm just going to chop it into 2 videos here. So let's do the next one. A cruise ship's captain sets the ship's velocity to be 26 knots at a heading of 080 degrees. So the 0 there tells me that it's a true bearing, right? There's a hint there. The current is flowing toward a bearing of 153 degrees. So that would be true bearing as well, at a speed of 8 knots. What is the ground velocity? So the resultant, right? We talked about in the note of the cruise ship. What is the resultant of the cruise ship? So we're going to be adding these 2 forces together. So let's do the green velocity to be 26 knots in this direction. And we're going to be adding that to 153 degrees at 8 knots of speed. What is the ground velocity? So let's look at, well, first let's just point out in red that ground velocity is the resultant. Let's do our scale and then let's do our diagram. So our scale this time, how long would things have to be? 26 knots and 8 knots. So obviously I can't draw, 26 centimeters. So I need my scale to be 1 centimeter equaling 6.5. I have in my notes 4 knots, but just like I said, it's not always beneficial to go too much more than 5 centimeters long. So you could make that more. You can make that 1 centimeter equaling 5 or 6 knots if you wanted to. And so then my 8 knots then would be 2 centimeters. That one's not a problem. 8 knots is 2 centimeters, but how much would 26 knots be? And again, you could just set up like 1/4 knots is equal to 26x if you wanted to. And that would be 6.5 centimeters that we're going to be drawing. So now we need our diagrams. We need to have our north-south and our west-east. I know the diagram is going to be going, because I've already done it, obviously, right to the right a bit more. So that's why I'm just drawing it that way, just to help you guys out with how you should do yours. So north, south, west, east, though I don't really need to have those labeled. And then I have, let's go with our direction here. So change to green. Cruise ship's captain sets the ship's velocity to be 26 knots at a heading of 80 degrees. So we know where 80 degrees would be, right? If I get my vector arrow here, right? If I was to start at north, right? I know that all the way here would be 90 degrees. So I'm just coming up a little bit more. And that's going to be the long one, right? That's the one that's 6.5 centimeters long. So let's say I'm going to draw that longer. And 80 degrees is quite a bit. So something like that. And then my blue vector is 153 degrees at a speed of 8 knots. I'll draw in the information afterwards, just since I'm on these arrows, right? Instead of switching, you might want to do it as you go, but just because of this program. And then I'm going in a direction of 153 degrees. Well, what's 153 degrees? So I've got 90 here, right? So if I were to take 153 minus 90, I would have an additional 63 degrees. So just saying, if my vector was like this and I was going down to 90, If I went all the way south, it would be 180. So I know that's too far. I need to go 153. So if I take 153 minus 90, it's an additional 63. So 63 is more than 45, right? So if let's say that's 45 to you, it's going to be a little bit more than that. So something like that. And 8 knots is much shorter, right? That's only 2 centimeters compared to 6.5. So that one's going to be shorter like that, let's say. Actually, the angle would be more, let's say like that. Like that. So then to finish my parallelogram, and then I'll fill in my information. I'm coming down like this. And I'm coming over like this. And then we have to look at, do I have 90 degrees going on in this diagram here? What information do I have? So I know from my green vector that it was 26 knots. I should be writing that in, right? 26 knots at a heading of 80 degrees. So I can just say here that from in this direction north to here is 80 degrees. And then for my blue vector, which is the current, it is 8 knots. So I can just write that. I wish I can't turn the page sideways, right? So I would write it like this if I were you guys and turn your page if you printed it out, but I'm just gonna write 8 knots here, indicating the magnitude there. And then to figure out my angle, right? All the way from the beginning to the end here is 153 degrees. So other angles that I could figure out though is if this is 80 degrees and this is the horizontal, then I know that this degree in here would be 10 degrees, right? In case I need to use that. And then I know that from 90 to 1, I know that 90 degree to 153, we already calculated was going down another 63 because I took 153 minus 90. So this from the horizontal down would be 63 degrees. But really what I care about is this entire corner, this entire angle from the green to the blue, right? So that entire angle there, I don't want to use red because that's the resultant. Hopefully you can tell the difference if I use pink here. From the green angle to the blue angle, how could I figure that out then? This angle, this corner, which would be equivalent to this corner here, right? According to the parallelogram laws. I would just take 63, because this was 63, and then add the 10. So this is 73 degrees, which would mean that this is 73 degrees. So therefore, meaning that they're not 90-degree angles. And also for the laws of parallelogram, right, we've got supplementary angle theorem here. So this corner here, just seeing if, yeah, I have room to write it. This angle here, supplementary angle theorem would be 180 minus 73. So that angle there would be 107 degrees, which again means that that corner is 107 degrees. We'll see if we need it in the diagram. I don't want to add too much in unless I need it to not confuse us any more than we need to, right? So first of all, it's not 90 degrees. I can't use primary trig ratios, and I can also not use Pythagorean theorem, right? So I have to choose which triangle to work with here. So again, usually we go from the horizontal. So whether it's at the top or the bottom, it doesn't matter. I have both of these angles here, and there's so let's just use, again, I'm just choosing one. Let's just choose the top triangle here. So, and have I not drawn my resultant in? I'm just looking, I'm more off than I was in my diagram, but the resultant would be going from the tail to tail corner. Oh, again, I wish I could just say reverse one step, can I? Because I don't want to, well, can I just, yes, erase that, perfect. Because I'd like it straight from this corner to the opposite corner. The resultant there is what I'm trying to get. So I'm looking at my top triangle here from the red to this side here, which is also 8 knots, which I can mark down. And then this is also 26, which I'll just switch to green. So from the red resultant, which we should mark R, to the 8 to the 26, we're going to use that triangle there. This is just my east horizontal, right? So I'm not going to be using that in the question yet. All right, so what do we know in order to figure out the resultant magnitude? I know that's not 90. I know that section's not 90. I know that this section of the triangle is not 90. So, and I have 2 sides given. So if I have 2 sides given, how can I figure out the resultant then? I do have, I don't have this side, I have this angle. I don't have just this angle from side 8 to the red resultant, right? So I'm just looking, I wouldn't be able to do sine law then. So what I need to do is use cosine law. All right, so for cosine law, which I guess I can leave red because it's to do with the resultant, right? So the resultant squared, so that side squared is, remember the beginning is just like Pythagorean, so 8 squared plus 26 squared. I'm just gonna, it doesn't matter which one you put first. Remember, minus 2 times 26 times 8. Then I need to figure out what it's the cos of capital what? So cos of the opposite angle to the resultant. So cos of 107. So then if I do my 26 squared plus 8 squared, I'm just going to do 26 squared and 8 squared together and add them. I get 740. And then if I do my negative 2 times 26 times 8, if I multiply those 3 together, the negative and the positive, you get a negative, plus another times another positive, you get a negative. I will have 416 cos of 107. And then I'm just going to stop here because I'm being reminded of what kind of mistakes do people make in grade 10, let's say when we're doing, and even in grade 11 and 11U. What could you see happening that will cause you to mess everything up from there? Don't write this down. Again, I'll erase this after, but this section here. So first of all, the 416 and the cos of 107 are stuck together, right? They're together as one term after the subtraction sign. So you can't separate them from each other. So again, I said, don't write that down. Oh, I'll have to fix that later. So to do, I do need to take a break. I'm getting tired. So this is 740 minus 416 cos. Okay, and back to black. If I were to do 740 minus 416 and get a value, right? And then some people then take it and multiply it by cos of 107, that would be incorrect because you're separating a term and you can't separate those. So I just wanted to make sure that you know, actually I'll leave it there like that and just put no, don't do this. So whether you want to write that down or not, whether you can remember if you've made that mistake in the past. So what I need to do then is calculate what, you might be able to do this all as one step in your calculator, but this is where you have to get to know your calculator, right? Figure out what 416 times the cos of 107 is. So then you'd have 740 just to show you step by step. And I have 121.6266, just because again, when you're doing trig, use at least 4 decimal places. I find will give you a more accurate answer. Well, hopefully your answer in decimals will match, let's say the back of the book or a worksheet that I was giving you. So now I have, again, the resultant squared is equal to, adding those together, 861.6266, which then the resultant is equal to the square root of 861.6266 is equal to 29.4. And we're talking about knots here in the question for the length for the magnitude. So 29.4 knots. We've got that. Now we have to figure out how to get our angle. What direction are we in, right? So again, if we look at we're labeling our theta there as being, that just says 10 degrees. So again, we're looking at, there's too many things here, but this angle here, right, as our theta, that angle there to figure out. How do I figure out what that angle is? So I have that angle, I have this angle, I don't have this angle, but none of them are 90. I can see that. And I have all three sides right now, but I can't use Pythagorean theorem not having 90, and I can't use primary trig ratios. But now that I have all three sides and an angle, I can use sine law. So let's just write down to find the angle theta, I can use sine law, and I'll show you here what I mean in a second. So I would have, let's say, 29.4 is the length of the resultant. So 29.4. And remember, the sine always goes with the angle. So what is the angle opposite to that? Sine of 107. And then I need to write down what I want to solve for. So this angle here, so sine of theta would go on the bottom over the side. The side is 8. Are you with me there for sine law? And then it's just a matter of cross multiplying, right? So always put the number in front of the sine of the angle. So 29.4 sine of theta is now multiplied together. The 8, the number itself goes out in front, multiplied by sine of 107. And if I wanted to get sine of theta by itself, I would divide by 29.4 and divide by 29.4. So then sine of theta would equal whatever this is as a decimal. And then you can take the inverse of that decimal, or I can just go ahead and write down here, just to erase this. Angle theta is equal to the sine inverse of all of this. If you're able to do that all in one step, awesome. If not, that's fine. You just have to get to know your calculator, or I'm just saying it might not be that bad of a thing to buy a calculator that works this easier way, right? And then you can keep it with you forever. So either way, if I had sine of theta like it was before and I just divided this, I would have got 0.2602 because I've done it that way. And then you're going to get the inverse of 0.2602. Or if you're able to plug all that into your calculator, you should end up with an angle. Angle theta equals 15.1 degrees. Okay, but again, we're talking about here when we go back up, we've got our magnitude, no problem. But for our direction, always go back up and look at the question that it was in true bearing, right? 0, 80 was the dead giveaway there. And 153 degrees, it doesn't say anything, it'd be from the north, right? Moving clockwise. So I need my answer to be in true bearing as well. So in order to make it true bearing, if I start from the north, right? And I know that I'm going to east, let's say is 90 degrees. And then it's continuing on below that for my resultant. And if I know that this part, so just stay with me here, right? From the horizontal up, this part of my angle was 10 degrees because I knew that this part was 80. So I know that from the black to the green is 10. So if that's 10 and the entire angle is 15.1, then I know that the rest is 5.1, right? Or 15.1 minus 10. So 5.1 degrees. So then I go back to north and that would be 90 degrees, right? Plus that extra 5.1 degrees, if you need to write that out. So for my therefore statement, sorry, I can see my writing is not the neatest, but I'm doing the best I can here. So it's asking for the ground velocity. That's how I should write it out. I shouldn't say, let's say just the resultant vector. So say the ground velocity is 29.4 knots. The ground velocity is 29.4 knots at, again, our 90 plus our 5.1. So 95.1 degrees north from north going clockwise. And again, if it is in bearing true north, true bearing, then I need to put the 0 in front because I need 3 digits there, right? The ground velocity is 29.4 knots at 95.1 degrees.